discuss briefly, giving an example in each case, about the role of coordination compounds in, well, you have 4 cases: biological systems, medicinal chemistry, analytical chemistry, and extractive metallurgy. Actually, coordination compounds or chelate complexes in general are so popular and so prevalent that every system has them, and there is no world, real world, without actually these complexes. But let's take a look in biological systems. Actually, of course, chlorophyll is very much there. It's a coordination compound containing magnesium ions, yes. So, central metal ion is magnesium, which is surrounded by a set of ligands, and that makes chlorophyll. It's a green pigment present in plants, I'm sure you're aware of that, and that is used in photosynthesis. Beautiful. Hemoglobin in your RBCs, because of which you're able to breathe. They are also ferrous complexes. Ferrous complexes which again form chelation, which undergo complexation with O2 molecules when you're breathing. I'm saying this off the record, one example is sufficient, but then again hemoglobin also is an example of a complex or a coordination compound or ferrous complex. Vitamin B12 consists of a tetrapyrrole pyrophyrin ring complex with a central cobalt ion and coordination number 6. Pyrrole rings are very popular, even hemoglobin has them. But in fact, it has imidazole rings. But nonetheless, we have 2 examples: chlorophyll with magnesium ions and vitamin B12 with cobaltic ions. We were asked for 1 example and we have offered 2. You can choose whichever you like. In fact, I just give you a verbal 3rd example also, hemoglobin. In medicinal chemistry, oh my God, you have cisplatin, which is used in chemotherapy in the treatment of cancer. Cisplatin is a dangerous compound, as I said, dangerous as well as, well, useful. Useful why? Because it is used in chemotherapy, and dangerous because chemotherapy is not only injurious to the cancer cells but also pretty much injurious to the healthy cells as well. What about analytical chemistry? Is complexation useful there? Very much. You get a number of complexes, like if you group 1 analysis, if you remember qualitative analysis, in group 1, what do? We add dilute HCl. And on adding dilute HCl, we are supposed to get white precipitates of either AgCl or Hg2Cl2 or PbCl2. How do we test them further? Add aqueous ammonia. If you add aqueous ammonia, silver in the form of AgCl is very much capable of forming a water-soluble complex or a coordination compound with ammonia as ligands. It dissolves in the solution, forming a colorless solution which contains the amine complex of silver. On the other hand, lead fails to form any such complex and remains unchanged. So, if the white precipitate on adding dilute HCl dissolves in aqueous ammonia, forming a complex, we say that this is quite a characteristic test for silver ions. No change means lead. If it turns black, mercury, but that is besides the point. Coordination compounds are not involved there, but this is an example of coordination chemistry. When AgCl used to dissolve, this is the reaction. Numerous examples can be given, but this is a very classic and the first elementary example from analytical chemistry or qualitative analysis, as they call it. In metallurgy, if you see, this some correction needed here. This is in metallurgy again, and especially when you are extracting gold or silver from ores. Now, gold and silver are present in really tiny amounts, and a lot of junk and rocks and soil and all kind of dirty things are there. If you wish to remove them and extract silver or gold, what do? You take all the ores, you wash them with a dilute solution of sodium cyanide, and you bubble air through them. And this activity actually dissolves silver as well as gold. Both gold and silver dissolve. Silver forms AgCN whole twice minus, and gold forms AuCN whole twice minus. There is a minus charge missing here. Let me add that. So, they come in the solution in the form of a dilute cyano complex. Then what do? You just filter it. All the soil, mud, rocks get filtered out. You have a clear-cut solution which contains complexes of silver and gold. You add zinc, destroy the complex, make a new complex of zinc, and take away silver and take away gold, and this is how you extract silver and gold from their ores. This is a very beautiful application of complexation or coordination compounds in extractive chemistry or metallurgy.